So let's talk about this first question, which is a survey of functional groups and sp3 and non-sp3 hybridized atoms. So I'm asking you to assign the hybridization of all non-sp3 atoms. So we did this a lot in laboratory. So first and foremost, let's look at this carbon here. So looking at this carbon here, what is the hybridization of a carbon with one double bond and two hydrogen single bonds? sp2, yep. This carbon is also sp2. To help everyone see that, let me draw out the implicit hydrogens found in this structure. Okay, what functional groups do we notice in this molecule? Alcohol, yep, alcohol. So that's our OH group. What other functional group do we see? What was that? Alkene. Alkene, yes, exactly right. We have an alkene, which is, oops, one moment, which is the carbon-carbon double bond. Perfect. The alkene is right here. Okay, let's move on to the next molecule. And drawing out our implicit hydrogens, what is the hybridization of this carbon here? sp, yep, has a triple bond, so it needs to adopt an sp hybridization in order to form two pi bonds. Additionally, what is the hybridization of this other carbon in the triple bond? sp, yep, has two sigma bonds and two pi bonds. Okay, what about the carbonyl carbon? What's the hybridization of that carbon with a total of 3 sigma bonds? sp2, exactly. And then finally, have we dealt with an alkene before? Yes. So what's the hybridization of these two alkene carbons? sp2, exactly. So now to list out our functional groups, we have an alkene, which is our carbon-carbon double bond. What other functional groups do we have? What do we call this triple bond? Yes, we also have a ketone. So we have an alkene, we have an alkyne. Oops, let me just switch over really quickly. Let me label this alkyne. Give me one moment. Let me switch to another page just because there's a bit of issues with the writing transmitting. Give me one moment to correct that and we'll be right back. Okay, so we have an alkene, we have an alkyne, and as our classmates pointed out, we also have this carbon-oxygen double bond functionality, and when we have two carbons attached to our ketone functionality, we call this a ketone. Okay, perfect. So we've labeled all of our hybridizations, we've labeled all of our functional groups. Let's now look at this last example. So, do we have any sp2 or sp hybridized atoms? What about in this ring here? What's the hybridization of the carbon atoms in that ring? sp2, exactly. We can tell that if we look at one of these carbons in detail. We have a total of 1, 2, 3 sigma bonds and 1 pi bond. Perfect. What about this carbon here? What's the hybridization of that carbon? sp2, exactly. Are there any other non-sp3 hybridized atoms? Technically, you can label the hybridization of this oxygen as sp2. That's acceptable. It's a little bit debatable whether it's sp2 or unhybridized, but if you labeled it as sp2, you still get full credit. Now let's identify functional groups. What do we call this ring containing a set of adjacent pi bonds. What do we call that? Arene, exactly right. So this is an arene. Okay, what do we call this NH2 functional group? Amine, exactly right. Finally, let's switch pen colors for this. What do we call this ketone functionality when it's attached to an NH2 group? So instead of an amine, it's an amide, yep, or amide, depending on your pronunciation. Yep, and those are all the functional groups found in this molecule. Okay, so very similar to what we did in lab. The next set, when we're asked for the lowest energy lone pair, what I want you to think about is lowest energy orbital. Right? Remember how when we drew all these orbital pictures, we were looking fundamentally at what is the energy of an electron in that orbital. And that's based on the atoms involved and the hybridization. Okay, so looking at this nitrogen here, what is the hybridization of this first nitrogen? sp2. Okay, what about this nitrogen in this case, cyanide? What is the hybridization of the nitrogen in hydrogen cyanide? sp, exactly. And then finally, in ethylamine, this is an sp3 hybridized nitrogen. Now, when we discussed hybridization, what are the lowest energy hybrid orbitals? Where do we in general see the lowest energy bonds, lowest energy electrons? sp, exactly. So we would circle this structure as it has the lowest energy lone pair. Does that make sense? Okay. Now, this next question, again, requires us to think about orbital energy. So in general, as our atom gets larger, what happens to our orbital energy? Increases, right? So if we put an arrow indicating increasing orbital energy, and the reason for that is you're going from, in this case, a 2p derived orbital to a 3p derived orbital, and finally a 4p derived orbital. As your orbital gets larger, your orbital energy increases, you're farther from the nucleus, and as a result, your electron energy also increases. Does that make sense? Okay. So which one would we circle? What's the lowest energy orbital? OH, yep. Perfect. So we're applying, yes?
Just out of curiosity, with the sulfur and hydrogen, is that an alcohol group?
It's a variant. Instead of an alcohol, it's called a thiol.
Okay.
Thiol for sulfur. Yeah. So a lot of the alcohol, or a lot of the oxygen-containing functional groups have sulfur derivatives that are called thiols or thioesters. So the thio prefix indicates that we've replaced oxygen with sulfur. Yep. They're smelly relatives of oxygen. Finally, in this case, we're asked to indicate the strongest carbon-chlorine bond. And as we've discussed time and time again, what affects bond strength? Bond length, yes, those are related, but so looking at each of these carbons, let's try to dissect this problem. So looking at each of these carbons, again, let's write out their hybridization. Let's think about what's different about each of these carbons. This first carbon is sp2, the second carbon is sp, and the third carbon is sp3, right? So then, as we discussed, what type of orbitals are lower in energy and form stronger bonds? sp, yep. So this carbon-chlorine bond is slightly stronger than this sp2 carbon-chlorine bond, which is slightly stronger than this sp3 carbon-chlorine bond. Because, remember, this bond involves orbital overlap, right? And the lower energy your orbital, the closer your bonding orbitals are to your nucleus, the lower in energy your resulting bond is, and the stronger and shorter that bond is. Does that make sense? So yes.
So lower energy is
Yes. Yes. In general, the more S character you have, the shorter your bond is and the stronger your bond is. And the reason why you can actually make this comparison is because the atom that you're bonding to, chlorine, is the same in all these cases. So this is an important effect of hybridization, not just on bonds between two atoms of the same hybridization, but bonds between your hybridized atom and other atoms in your molecule. So hybridization has an effect on bond length and bond strength. It's not just the fact that we're forming more bonds, but the fact that the atom has a specific hybridization and those orbitals have a different energy. Does that make sense to everyone? We saw examples of this on the homework when I asked you to dissect carbon-hydrogen bonds. Any questions on these examples? Okay, let's now finish up chapter 1. And when we last left off, let's go over. When we last left off, we talked in detail about constitutional isomers and condensed structures. Let's now drill down into the idea of condensed structures, and let's talk a little bit about how to effectively write condensed structures and some rules on what you can and cannot do for condensed structures. So, if a portion of the formula has a subscript, such as, for example, CH3, 2, the subscript indicates the number of formula subunits attached to the carbon chain. So, when we see this CH22, let's give a full example. If we're looking at, for example, CH, CH22, what we're saying is these methyl groups, these CH3 groups are attached to our central carbon. So we draw our carbon, we draw our one hydrogen, and then we draw our two CH3 groups attached. So this is our way of condensing and indicating the number of attached side chains to one of our carbons in our molecule. Does that make sense? Do you notice how we have two CH3s, so we draw two CH3s? So the subscripts indicate the number of structural units attached to one of our carbons. It's a really nice way of avoiding having to write a lot. So the carbon containing a functional group or attached to a formula subunit will have less hydrogen atoms than an unsubstituted carbon. So what do I mean by that? So let's look at 2-methylbutane. So 2-methylbutane. This is its full Lewis structure. So we're going to partially condense the structure by avoiding having to write all of these carbon-hydrogen bonds. Yes? What it's implying is the position of this methyl group, and we'll talk more about that actually in chapter 3. So this is classic, the IUPAC name for this compound. It has nothing to do with the number of methyls, but it has to do with the position of the methyl group. What is interesting in this molecule is after we partially condense this molecule, we've avoided having to write all of the carbon-hydrogen bonds. We're now going to further condense this formula by indicating the number of side chains attached to each carbon. So for example, if we look at this carbon on the far left, it's attached to, if we look at it from the perspective of a box, it's attached to one thing, right? So how many hydrogens does it have? How many hydrogens are in this CH3? 3. Yeah, so it's attached to one thing, so it has 3 hydrogens. 3 plus 1 gives us 4. Now, if we look at this carbon here that contains both of these CH3 groups, how many things are attached to it? How many things are attached to this poor carbon? How many total carbons are attached? 3. So we have 3 carbons, and in order for us to get a total of 4 bonded atoms, how many hydrogens are attached? 1. And whenever you see a carbon with less hydrogens than normal, less hydrogens than expected, if you just had single bonds, that is a sign that you have multiple substituents attached, such as multiple CH3 groups, or you have a functional group attached to that carbon. Does that make sense? So the carbon with less hydrogens than normal indicates that something else is attached to that carbon, such as a CH3. Does that make sense? Now, what we can do is we can abbreviate this carbon containing multiple substituents as CH. So we're going to write this carbon as CH. Now, how many CH3s are attached? How many CH3s do we see attached to that carbon? 2. So then, since it's at the end of our chain, we're going to write CH3, 2, to indicate we have 2 of these CH3 groups attached to this carbon. And the way we can tell that they're attached to this specific carbon is because it has less hydrogens than a straight chain carbon. Does that make sense? Does everyone notice if you compare these 2 carbons, under normal bonding conditions, we would have a CH2. Since we have something else attached to our carbon, we have a CH. Does that make sense? So this is how you know where to place your functional groups and where to place your chains in condensed structures. So let's take a look at writing out a condensed structure. Let's take a look at doing this process in reverse. So I'll show you the step-by-step process. So first and foremost, I'm just going to read my formula from left to right. So what's the first thing that we see in the formula? CH3. So I'm going to write a CH3, a carbon with 3 hydrogens attached. Okay, what is attached? What's the next thing in our chain? Reading from left to right. Yep. With how many hydrogens? 2. Okay, now we're getting a little bit fancy. What's next? What, just a carbon, right? Okay, and now we have this CH2OH to work with. And how many of these CH2OHs do we have? How many of them do we have attached to that carbon? 3. Okay, so I'm going to write out my first CH2OH, my second CH2OH, and then finally my third CH2OH. Perfect. Is the octet rule obeyed for all of our atoms? Does each carbon have 4 bonded atoms to it? Take a moment and take a look at it just to verify. Yes or no? Yes, yep. This carbon, 1, 2, 3, 4, we put a check. 1, 2, 3, 4, we put a check. 1, 2, 3, 4, we put a check. And the way that we know to put these side chains on this carbon is the fact that, does this carbon have less hydrogens than normal? Yes. And also, reading from left to right, this set of side chains comes right after our carbon. So you have your carbon, and then what's attached to your carbon right after. Does that make sense? Okay. So there are nice little shortcuts that we can use to avoid having to write out super long chemical chains. So the first major shortcut, if a formula unit is repeated, it can be abbreviated using a subscript. So for example, notice how we have CH3, CH2, 2, CH3. So this is a really long carbon chain. instead of having to write out 2 CH2 subunits, we abbreviate it with a subscript. So if we're expanding this out, we'd write a CH3, and then what is attached to the CH3, reading from left to right? CH2. Now, why do I not put a second CH2 on this carbon? Exactly right, exactly right. So then, where do I put my second CH2? On the next carbon, exactly. And then finally, we put a CH3. There we go. So we've expanded out this CH2 into the full formula. So this is the uncondensed formula. Well, this formula here is condensed. Does that make sense to everyone? Okay. So you're more than welcome to condense your formulas to save writing space and to make it easier for you to quickly transmit ideas. Okay, let's now do some examples. Let's do some examples. So in this case, we're going to write a condensed formula for each structure. And I also want us to identify the functional groups in each structure. Don't worry about writing alkane every single time. Those are sort of the fundamental building blocks of all organic molecules. It's redundant. I'll write it for this first one since this molecule is pretty boring. So this molecule clearly is an alkane. It just has carbons and hydrogens with only single bonds. Now, if we're reading from left to right, what I like to do is I like to look at my left-hand side of my chain, my right-hand side of my chain, and the middle of my chain. Okay, so starting from the left, what should I write? What functionality is on the left? CH3, exactly right. Okay, now for in the middle, what functionality do we have? CH2, and we have 1, 2, 3, 4 CH2s. So can I abbreviate those CH2s using a subscript? And what subscript should I put? 4. Because I have 4 CH2s. And finally, to cap off my chain, what do I put? CH3. Perfect. Let me show you an example where you'll have to get a little bit creative. So we're going to look next at this example here, just so that way you have a representative example for the major cases that you'll see. So what I'm going to do is I'm going to start from my left-hand side. So on my left-hand side, I have a CH3. Perfect. What is attached to that CH3? What is attached? What's adjacent? CH. Okay, and what functional group is attached to my CH? Alcohol. So I'm going to put that in parentheses. OH. And now I'm going to continue on with my chain. What's the next thing in my chain? CH2. And then finally, what caps off my chain? CH3. So you will commonly see functional groups in the middle of your chain placed in parentheses. Organic nomenclature, which is the act of naming organic molecules, has a much more elegant solution for representing these formulas. But for now, this is our way of conveying chemical formulas without having to write out every single Lewis structure. Does that make sense? So you should, I'd like you now to attempt these next these next 4 examples for now, and we'll move on to more of them. Actually, if I can make space, here we go. We now have 5. So let's work on these 5 and write out condensed formulas for each of these 5. As a side note, in condensed formulas, you are welcome to draw double bonds if you want. But I would encourage you to practice without having to draw double bonds. Any questions? You can do them using subscript notation. CH2. Yeah. Everything going okay? Okay. Everything going okay? Yeah. Yes. Yes, yes, exactly. Yeah, perfect. Everything going okay? Looks good so far, but since we have a repeating common unit on both sides, can we use subscript notation?
Maybe this too.
Yes, yes. And but you put the nitrogen first. Well, that's just oh yes, yeah, for that one?
For that one.
For the oxygen goes last. Yes, that's correct.
All right.
Yep, that's perfect. Everything going okay?
Good. I think I just have to. So
And you
this
can
one,
abbreviate
the first.
Yeah, you can abbreviate the Q units. And just make sure you're counting your CH2s. Should only be-
Oh, and this one?
Yeah.
Was it-
Well, there's one each, yeah. Oh, I see what you did. The subscript just doesn't include both CH3 and CH2. So it's very close.
So CH3, CH2. Oh, can I use CH3, CH2?
Oh, you write the CH3, CH2 together in the parentheses,
Oh.
because it's repeated.
Oh.
So that makes sense?
Yeah.
Perfect. Any questions? Yeah, and the way we write aldehydes is HO. Yeah. OH are alcohols, HO is aldehyde.
Okay.
Yep.
Thank you.
So I'm seeing a lot of reasonable answers. Let's just take a look at a few of these. Just to go back to my previous example, this has an alcohol, the OH functional group. Let's start with diethyl ether, which is something you'll be working with a fair amount in this class. Now, I always like to look for symmetry in my molecules because that allows us to simplify how we write out the condensed formulas. So as we notice, on the left and the right-hand side, do we have the exact same arrangement of carbon atoms? Yes. So what is that arrangement? From left to right, what's our first motif? CH3. Okay, and attached to that is what? CH2. Okay. Now, attached to this CH2 is what? An oxygen. Now, if we keep reading on the right, do we have a CH3, CH2 on the other side? Yes. So how many CH3, CH2 chains do we have? 2. So can we abbreviate that with a subscript of 2? Yes. So this is common for functionalities found in what are known as ethers. This ROR, carbon, oxygen, carbon, single bond arrangement is known as an ether. This is often where this symmetry and this method of condensing ether formulas comes into play. Yes?
Doesn't matter which side the oxygen is on.
In general, the oxygen is placed on the right-hand side in the formula, and that's stylistic. Let's now look at an amine. Let's now look at an amine. Is this amine also symmetrical? Yes. So we have a CH3 and a CH3 on both sides. So we have how many CH3 groups? 2. And they're attached to what functionality? NH. And for amines, and this is purely stylistic, the nitrogen goes first because these 2 substituents are attached to our nitrogen. So we call this an amine. The key signpost for an amine is the NH. Let me switch pen colors. Yes,
So even though it's just NH, that's still classified as amine, it doesn't have to be NH2.
it doesn't have to be exactly NH2, as long as it's a nitrogen with just single bonds surrounding it, and it has a free lone pair. Yeah. And there are different types of amines depending on the amount of carbons attached to the nitrogen. So amine, I just want you to think NH. Yes.
So then, sorry, would an
Oh, yeah.
amine be a nitrogen with 2 bonds instead of the 1?
So what do you mean?
Or would the amide be a nitrogen with 2 bonds?
Oh, the distinction between amine and amide. So let me use a different pen color for that. So an amide is a carbonyl derivative where you have this NH2 or NH adjacent to a carbon-oxygen double bond. So an amide is a derivative of a ketone functionality. Does that make sense? Perfect. Okay, let's now look at a pretty fun molecule, 2-butene. You've been seeing a lot of symmetrical molecules, and this is just to get you in the habit of condensing repeated chemical formulas using this condensed structure notation. So in 2-butene, do we also see repetition? Yeah. So we have on the left-hand side, what series of atoms do we have? Yep, so CH3, and then what's attached to that CH3? CH. Okay. Now I'm going to write out the full formula for starts, just so that way you can see something that's pretty interesting. There are 2 ways of portraying this formula using condensed structure notation. The first way is just straight writing out the atoms and the number of carbons and hydrogens. That's one way. The other way that you are permitted to use is you can explicitly show, oops, one moment. Let me change pen colors for this. You can explicitly show that there's a double bond, and this only applies for double and triple bonds. I would like you to be used to writing structures without having to explicitly draw the double bond, but you are welcome to use this method as well. How do we know that there's a double bond between these 2 carbons? What do we notice is unique about these 2 carbons? Yes, they have less hydrogens than normal. And that's your signpost. Something is there. In this case, a double bond. We call this double bond an alkene. E-N-E. Does that make sense to everyone? Okay. The final way that you can abbreviate this structure is due to the fact that it has a unique repetition in its chemical formula. You can abbreviate it as CH3CH2. But this is only applicable if it's symmetrical. Notice how it's exactly the same on both sides? That only works for symmetrical molecules. There are plenty more examples, but let's touch on these 2, Acetani Trial and Acetaldehyde. So let me zoom in on those. And the reason why I chose these examples is to give us as broad of a review of functional groups during this section as possible. So let's look at Acetani Trial now, and allow me to switch pen colors. Okay, so taking a look at Acetani Trial, what is the first functionality that we see? CH3. Yep, so the first thing that we see is CH3. Okay, perfect. What is attached to that CH3? Yeah, a nitrile functionality, but what is attached in terms of atoms? Carbon, yep. And then what is attached to our carbon? Nitrogen. Okay, CH3CN. You can also draw it with the triple bond, like CH3C triple bond N, but this method is far more common. And we call this CN functionality a nitrile. Any questions so far? Everything going okay? Okay, let's now talk about aldehydes and acetaldehyde in a little bit of detail now. So let's take a look at acetaldehyde and let's try to write out its condensed formula. As it's a very simple molecule, but there's a small subtlety in writing out its condensed formula. So what's the first functional unit we see? CH3, yep, a lot of repetition of that. CH3 is a pretty common starting functional unit. Now, what do we call this ketone-like functionality, but instead of being attached to two carbons, it's attached to a carbon and a hydrogen. What do we call that? Aldehyde, exactly. So it says so in the name. This functionality is an aldehyde. And the way that we abbreviate aldehydes to differentiate them from, for example, an alcohol is we write them as CHO. So anytime you see this CHO, that's a key signpost for an aldehyde. Does that make sense? And the other way that we can tell that this carbon is an aldehyde, does it have less hydrogens than usual? Yes. Your alcohol, if it was written in this manner, would be written as CH2OH. So there's a clear distinction between aldehyde and alcohol in terms of their chemical formulas. Always just keep in mind, you need to be able to read these condensed formulas so that way you can understand what structure is being conveyed. There's a huge difference in properties between aldehydes and alcohols. Any other questions on this condensed structure practice?
Just one quick.
Yes.
Based off, I mean, I don't know if this is just like you can choose whatever one, but like
Sure.
say for example the N-hexane. You have
Yes.
this the CH3 on either side.
Yes. You
and
can
then-
start from either the left or the right. There is no inherent preference at this time.
All right, I guess what I'm saying is like say compare that one to the diethyl
Yes.
ether,
Yes.
where it's like we just squished it all
Ah,
together
yes.
and then
And
threw a
the
substrate on it.
reason why we were able to condense it via symmetry is due to the fact that in the middle of many of these molecules, there's a unique functional group. And it's because they're symmetrical about the functional group can we condense the formula around them. Does that make sense? So like in N-hexane, there's no functional group to go off. So instead, we do our best and we condense these CH2s in the long chain. In general, for long chains, you condense the CH2, which we call methylene functionalities, while in compounds containing functional groups, if they're symmetrical, you condense your formula around your functional group. Does that make sense? Perfect. So let's now continue on and let's elaborate a little bit further. So now what we're going to do is we're going to draw the Lewis structure for each of the condensed structures. So we're reading condensed structures and we're writing out valid Lewis structures. Additionally, if we can identify the functional groups, that saves us a ton of time in writing out valid Lewis structures. So what I'm going to do is I'm going to utilize the method involving bonding preferences. So we're going to read the formula from left to right. We're going to try to identify functional groups and then write out the bonding patterns based on those functional groups. So what's the first thing that we see? CH3. Okay, what do we have to transcribe next? How many CH2s? 2. So I'm going to write CH2, CH2. What is attached to the CH2? Yep, an oxygen. And then we have a CH3 functionality. Now, how many lone pairs must be on that oxygen if it has 2 bonds? 2, yeah. Okay, so we've started to expand out this condensed structure, and the key thing, we've written out the number of lone pairs needed to satisfy the octet for oxygen. Finally, what do we call this bonding arrangement, this carbon-oxygen-carbon arrangement? Ether, exactly right. So this is known as an ether. Carbon, oxygen, carbon. Let me switch pen colors, one moment. Okay, what I want you to do now is I want you to tackle drawing out Lewis structures for the following 3 molecules. So take a moment and try to quickly expand out these condensed structures and identify the functional groups. If you can identify the functional groups from the formula, it makes it substantially easier to draw out Lewis structures. Because remember, functional groups are fixed arrangements to atoms. Everything going okay? Yeah, pretty fast. That'd be good. Everything going okay? Yep, looks good. Everything going okay? Yes. Yes, exactly. Not yet. There's no, there is perfectly symmetrical, so it doesn't matter. And if I wanted to delineate that, we use methylene notation and stereochemical notation. So, yeah, looks good. Everything going okay? Yeah. Okay, perfect. Everything going okay? Okay. So, what is the CHO functionality? What kind of functionality? So that corresponds to an aldehyde. And then try to expand out the aldehyde into the correct bonding arrangement for that function. So that CHO is telling us we have this carbon double bonded with oxygen bonded to hydrogen. Does that make sense? So all you're doing is when you recognize the functional group, you write out the bonding arrangement for that functional group matches. Does that make sense? Give it a try. I'll be back to check. Just be a little bit careful and think about let's attach that carbon. But it's very close. So the one distinction is that thinking about the number of hydrogens that would need to be attached to this carbon in your structure. So you've given out the formula for an alcohol, but looking at our arrangement in this formula, CHO, is that an alcohol or an aldehyde? Yep, but it's very close. Yep, looks good. Looks good. Yep. Everything going okay?
I'm struggling with this one.
So how many things are attached to the middle carbon?
Because it's attached to the oxygen.
Yep. And what about these CH3s? Are they also attached to the carbon?
That's correct.
Yes.
Oh,
So
I see.
everything is on the carbon. Everything going okay? Just try to think what is attached to this carbon. Doesn't have any hydrogen on it, right?
Right.
So how many things must be on it?
Both these
Yes. And the others. How many of these CH3s?
Okay.
Yeah. Exactly. And that's why I always like counting my hydrogens. It tells me how many things are around my carbons. Okay, thank you. So let's talk a little bit about a few of these. I know we're going a little quickly, but that's why I have additional examples for you to practice, and that's why we're doing a lot of examples together. Practice makes perfect. So CH3CHO is actually an exact repeat of a structure that we've dealt with previously. So reading from left to right, what's the first functionality that we write? CH3. Okay, now CHO, is that an aldehyde or an alcohol? Aldehyde. So CHO corresponds to a carbon double bonded to oxygen, bonded to a hydrogen. We call this functionality an aldehyde. The other way that you can tell that it's not an alcohol is this carbon. Does it have less hydrogens than usual? Yes. Okay. This next structure, if we look at this central carbon, how many hydrogens does that central carbon have? 0. So how many things must we have attached to that carbon? How many things? 4. This carbon has 4 things attached to it. So what I'm going to do is I'm going to attach both of my OHs, right? Since I have 2 of them. What else is attached to this carbon? What other functionalities do we have? CH3s, and we have 2 of them. Now, for those who are asking, why don't I just string my CH3s together back to back and call it a day? What is a problem with something like this? What's a problem with something like this? Carbon has too many bonds, so it wouldn't work. So anytime you see multiple CH3s, they must be hanging off of your chain or at the end of your chain. Otherwise, you break the octet rule. Does that make sense to everyone? And what do we call this OH functional group? Alcohol. And then finally, to add in our lone pairs, how many lone pairs do I need to put on this alcohol oxygen? How many lone pairs? 2. Because oxygen wants a total of 8 electrons. So we have 2 bonded atoms and 2 lone pairs. Does that make sense? Let's do another example. This one I really like because it's quite interesting to dissect. So I've clearly showed you that there's a double bond, right? So I'm going to draw that first. That's the easiest for me to read, so I'm going to draw that motif first. Now, my question to all of you is, how many bonds are attached to this carbon with 0 hydrogens? Oh, I mean, how many total bonds? How many?
Oh, no, it has to fall, right?
Yeah, it has a total of 4. So it needs 4 things. We already have 2 bonds on this side, right? So what are these CH3, CH2s attached to? That carbon, exactly. So this is another type of symmetry, and another way of condensing structures that you can see is that if you have the same substituents on one side of a double bond, you can condense those substituents, right? Do you notice how both of these chains have the exact same formula, and there are 2 of them? Yeah. Does that help? So what do we call this functional group, this double bond? Alkene. Exactly right. Okay, perfect. So we're now starting to be able to interpret written condensed formulas. Let's now continue on and talk about further methods of simplifying how we portray molecules. So, with this idea of condensed structures in mind, and with this idea of functional groups in mind, we now have enough information to develop some rules to quickly write constitutional isomers. So, The fastest way to make a constitutional isomer is to swap a functional group or carbon chain on one carbon with a hydrogen on another atom. But there's one thing that you need to check when you're drawing constitutional isomers. And what I want you to do is to number your carbons. And I like to use two different colors for this. On the first case, I'm going to number them from left to right. In the second case, I'm going to number them from right to left. This is our check to make sure we have not just rotated our molecule. And you'll see how this works in a moment. So you're going to swap your functional group and your hydrogens between two carbons with different numbers for both counting methods. We'll show how this works in a moment. And for those who are wondering, why do I have to count from left to right and right to left? What is the purpose behind this count? Well, a constitutional isomer has a different connectivity of atoms, right? We have a different arrangement of bonds in terms of what atoms are connected to what other atoms. If you can rotate the molecule to give the same structure, you do not have a constitutional isomer. So then, what this counting method does is if your functional group has the same carbon number, your connectivity has not actually changed. You've just rotated your molecule around. So let me show you how this works in practice. So I'm going to start with a dark pen, so that way we can see our base chain. So if I'm asked to draw constitutional isomers for CH3, CH2, 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 OH. Okay, perfect. So to make this a little bit easier on myself, I'm going to show each of the possible hydrogens I can swap. Okay, perfect. So I have each of the hydrogens I can swap. Now I'm going to number my carbons. Now I'm going to number my carbons. One, let me switch pen colors correctly this time. Perfect. Okay. 1, 2, 3, 4. Okay, perfect. So that's my left to right. Now let's do right to left. 1, 2, 3, 4. Perfect. So I am free to switch the position of any OH with any hydrogen if the number in red and the number in blue are different, if they're different, okay? So then, I'm going to take this OH and can I swap it with this hydrogen here? Would that work? Are the numbers in red and blue different? Yes. Okay. Could I theoretically swap it with this hydrogen? Is that okay? Are 3 and 4 different? Yes. Right? Because the number in blue and the number in red are different. Does that make sense?
Can you repeat that one more time?
So if the number in blue and the number in red are different, you can swap them and you get a constitutional isomer. If they're the same, you cannot swap them. You'll just be rotating your molecule. Yes.
On the top and the bottom, you can count the carbons, right?
Yes, yes. One from left to right, the other from right to left.
So in this molecule, you can pretty much swap it with any of them because it won't.
Except for this last hydrogen. And let's showcase that. And that's a wonderful lead-in, actually. So let's highlight that. So let's switch to a different color. So if we try to swap the OH with the farthest hydrogen down the chain, looking at our number in red and blue, are they the same or different? Same. So can we swap them? No. Now, let's show the results of each of these swaps, so that way you can see for yourself what's going on here. So let's go down a little bit and let's show the results of each of these swaps.
So you use the number that's closest to the,
You compare both the red and blue number, and if they're different, you can swap. If they're
but
the
it's
same,
always the red that's closest to what you're trying to swap, right?
it's the red number we're using is the number of the carbon that the alcohol is attached to.
Gotcha.
Yeah. So let's show the results of each of our swaps and let's see what we can see. So suppose that we did the swap that was not permitted according to this rule. We would get the following structure. Are these structures exactly identical except rotated? They're exactly identical. The only thing that's been done is this structure has been rotated 180 degrees. So these two structures are exactly the same if we performed this swap. So are these two structures constitutional isomers? No, they have the same connectivity of atoms. Let's put an X through that. Let's look at our other valid swaps. So we could have CH3, CH, OH, CH2, CH3. Is this a valid constitutional isomer? Yes. Let's look at our other potential swap, and you may notice something a little bit interesting here. You may notice a little bit interesting. So if we compare these two possible constitutional isomers, have I drawn the same molecule again? Have I drawn the same molecule again? Yes. Same relative connectivity.
It has to be 3 and above in order for you to.
So the reason why that is, and the reason why these two molecules are the same is because we'd essentially be switching the alcohol from carbon 3 to carbon 3. So the numbers are the same, so the swap isn't allowed.
Yeah, so let's say that there was CH2, and.
Then you'd have a lot more possibilities because then the molecule wouldn't be symmetrical. Does that make sense? Perfect. So I like this method because it's very procedural and it beats having to guess and check. So it's fast to draw constitutional isomers. Let's do some practice now. One other way that we can draw constitutional isomers is by exchanging a carbon chain or subunit with a hydrogen atom or functional group. So we can also exchange entire functional groups or sets of carbon and hydrogen atoms. So just like before, we're going to use the exact same numbering method. So if we have CH3, CH2, 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 OH, this time we're going to think, how can we creatively move our carbon substituent? How can we creatively move our carbon substituent? Okay? So to do that, again, what I'm going to do is I'm going to write out all of my potential hydrogens that I could swap with. And that way, it's really clear to me what I'm doing. Okay? What? Oh, because I've taken one of the hydrogens and I've drawn it as an explicit swappable hydrogen, just to make it easier for me to see what I'm switching. Next, I'm going to do my numbering. So I'm going to go from left to right. 1, 2, 3, 4. Okay, this time I am numbering my oxygen because it is a potential atom that I can swap my methyl group with for a hydrogen. I'm going to also number it and number all of my carbon atoms in the opposite direction. Whoops, let me switch pen colors. One moment. Perfect. Okay, so let me number it from right to left. 1, 2, 3, 4. Okay, so let's think of all the places that I can move my methyl group. Are there any swaps that are there any problematic swaps here? Are there any problematic swaps here? So can I put this methyl group on this carbon?
Yes.
Yes. Can I put it on this carbon?
Yes.
Yes. Can I put it on the oxygen? And this is one case where the rule falls apart a little bit. Let's think about what happens when we put it on the oxygen. What happens if I decide to swap this methyl group with this hydrogen? And let's draw the structure out. Do we get a constitutional isomer? Let's show this. So in this case, we'd have a CH3, CH2, CH2. So CH3, CH2, CH2, O, CH3. So are these two structures constitutional isomers? Do they have different connectivities? Yes. So we're good to go. This is a structure that allows you to perform multiple swaps of this methyl group and still end up with a constitutional isomer. Yes.
So when you want to go back, I'm trying to remember, you want to pick the number that's not necessarily as closest to or the
You just want them to be different. As long as the number in red and blue are different, then you won't end up producing the identical molecule when you switch. What these numbers are doing is they're checking for symmetry. And essentially, for constitutional isomers, when you switch a carbon chain or a functional group and a hydrogen, you're changing the connectivity of atoms. And if these numbers are the same, what that's telling you is when you switch these two functionalities, you will end up just rotating your molecule. The atoms will be arranged in the same connectivity. Does that make sense?
Yeah, I get that, but I'm just trying to remember how you said that. How do we tell when it's the same, when the numbers are the same?
If the number in red and the number in blue are exactly the same, then you're not allowed to swap a substituent on that carbon.
I get that, but what I'm saying is how do we know which one to pick? That's what I'm saying. Like,
Oh, you can pick any of them. You can switch any substituents. We're just looking at the fact you can switch this methyl around to get a constitutional isomer.
I don't think you understand what I'm trying to say, and I don't know how to say it, so okay, that's fine.
So like we can swap this methyl. We can also, as we've entertained earlier, we can also think about how we can swap this OH around. This is just a method to procedurally generate these constitutional isomers, and it doesn't actually matter which one you pick. You can pick any functionality or any chunk of the molecule you want. Does that make sense?
Yeah, I get what you're saying. I don't know how to ask my question.
It's okay.
So.
I can address it after class.
Yeah.
Okay, perfect. The last way that we can make constitutional isomers is by exchanging non-hydrogen atoms. So another way to generate constitutional isomers is by exchanging the positions of non-hydrogen atoms. And in this case, we often don't have to worry too much about our numbering scheme, but let's just showcase how this method works. So we have our same chain that we've been looking at throughout this study, okay? And our goal is we're going to think about how we can swap the oxygen and the carbon atoms. Okay, so we're thinking about swapping oxygen with one of these carbon atoms. Does that make sense? Okay, so let's break out our numbering scheme. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So what this numbering scheme is telling us is looking at this oxygen. we can swap it with any position that has a different number to either of its two numbers. So for example, looking at the blue, I can swap it with anything that has a red number that's not 1. Because if I swap this oxygen with this carbon, would I just end up rotating my molecule? Yeah. So if the number in blue and the number in red are the same, you cannot swap. If they're different, you can. So let's showcase an example. Which carbon do you want us to swap the oxygen with? Which one? 2. This one right here? Looks good to me. So let's swap them. The reason it's okay, 1 and 2 are different. Okay, so we have CH3, and because I've swapped this carbon and oxygen, what do I put? If I swap the carbon and oxygen, what's now there? Oxygen. So let's just put the oxygen there. Then we write CH2, CH2, and then finally, what ends up at the end of our chain? CH3. And as we notice, this molecule now has a different connectivity. Does that make sense? Of course, if you're more than welcome to try just swapping atoms and functional groups and then checking your work. The reason why I like this procedural method is that it's very useful when you're first developing the intuition. What structures are symmetrical? What swaps are allowed? Yes.
So in this case, are we moving the 2 hydrogen with the carbon?
Yes, just so that way the octet rule is fulfilled. Yes.
So is it always okay to choose to swap the oxygen when it's presented as a weight?
Yes, yes. For constitutional isomers, this is just a method of quickly rearranging the bonds in your molecule to generate a new connectivity.
So like in our first example, how we swap OH both.
Yes, you can swap the functional group of OH, or you can swap individual atoms. Both are fine. Let's check our time. We have a few more minutes to do some examples. So what I want you to do as an exercise is I want you to draw all constitutional isomers for the following formula. And I'll write it out large so that way everyone can see it. So CH3, CH2, NH2. So a nice, simple, and sweet one. You should end up with about 2 or 3 constitutional isomers. The more the merrier. Any questions? Oh, good, good.
No, so it had a moment where
Oh, yeah. And one
I was
node
gonna
is a
say
little
to you,
quirky.
oh, but for this one, similar to this one, where we just move the oxygen, would that be the same case as this for CH3 and CH3
Yeah.
again?
Yes, yes, exactly. So in this case, you're doing an atom swap.
Okay.
Yes. Mhm. Yeah. Yeah. With nitrogen, because the blue and red are the same. Yes, exactly. Yes, that's exactly right. Except just make sure to change this to NH and use CH to CH3, just to ensure the octet is fulfilled. Yeah. And the reason why I like this method is it makes a lot of the implicit thinking explicit. Ah. Oh, okay. Yeah. Any questions? Everything is going okay?
Oh, yeah, I can, so it will be 3, right? 1, 2, 3.
Yes.
So it is, And this is where I have a question, another question. You just assume that this one is on one, or?
Yes,
Or any
and
number.
it doesn't matter, and as long as you're counting from left to right and right to left. But since it's at the end, I'm gonna call it 1. Yes. Yep, that's good. Yes. Yes, they're,
Yeah, I mean, I guess you can't really move it to the first one, but it changes, like, say, like I did. I don't know if it changes if we do the whole thing.
yeah,
So I was thinking of the method of, is this one side groups?
yes.
So then the first one should be,
Yeah, so,
that won't work.
yeah, exactly.
Because it'll just be opposite.
Yes, exactly.
Okay.
Yep, exactly right. So I misspoke. There's actually only one for this structure. You'll be dealing with a very similar formula with substantially more constitutional isomers. So just to showcase our numbering method, I'm going to think about it from the perspective of atom swaps. So 1, 2, 3. 1, oh, why is this the same color? One moment. Okay, 1, 2, 3. Okay, so as we can see, what carbon can we swap this nitrogen with? Where do we see different numbers? The middle one? Yeah. So we're gonna swap this carbon and this nitrogen. And that gives us the following formula: CH3, NH, CH3. Oops, one moment. There we go. So that's the only constitutional isomer that we could potentially draw. Were there any other potential isomers that you'd like us as a class to evaluate? No, that's the only one we could think of. We'll be doing more practice next class session. We're definitely going to be blazing through the end of chapter 1 as the remaining topics are pretty fast. I'd like you to read up in your textbook on bond line structures and intermolecular forces, and I want you to start looking at chapter 2. Okay.